Hello, sir.
Can you hear me?
Okay, sir. Yes, sir.
Yeah. Yeah, tell me.
Okay, sir. Can I start, sir?
Yeah, of course. Let me find out how to. Yeah, share. Yeah, you can. Go ahead.
Okay. So, good afternoon, all of you. Today, afternoon session, uh, it is taken by Dr. Manoj Neergat, sir. Uh, First of all, I introduce Dr. Manoj Neergat, sir. He is a professor in Department of Energy Science and Engineering at IIT Bombay. He did his PhD in 2001 from Indian Institute of Science, Bangalore. After completing his PhD, he was postdoctoral fellow at the Technical University, Munich, Germany in 2003.
Yeah, I'm in a lecture today.
After that, he joined LN Laboratory USA,
which I committed to even before.
and then after he joined CECRI Chennai in the year of 2006
So I
as a
finished
QHS fellow.
1.5 hours lecture.
Then after he joined the Department of Energy Science and Engineering, IIT Bombay in 2007 as an assistant professor. Since then he has been at the same institute and he is a full professor since 2016. He has been involved in the development of electrochemical energy conversion and storage device and has extensive experience in the synthesis and electrochemical characterizations of various energy related materials. He teaches various energy related courses at the institute to both undergraduate and postgraduate students. Now, welcome to Dr. Manoj Neergat, sir, for your expert session.
Okay.
Sir, any
Just
problem?
wait. Can you hear me?
Yes, sir.
Just wait a minute. Let me organize.
Okay.
Yeah. So, are you able to see my screen? No.
Yes, sir.
You're able to see?
Yes, yes, sir.
What do you see?
That is the fuel cells. Good
Okay.
afternoon.
No problem. No problem.
Welcome to
Yeah. And let me see one more window. Okay. Stop the sending window. And are you able to see this window?
Yes, sir.
Is it a slide?
Yes, yes.
PowerPoint?
Yes, I'm fine.
Is it covering your screen?
Yes, sir.
Okay. 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 How many participants are there?
It's more than 62.
62.
Mm.
Wow. 62 people are listening to me now?
Yes, sir.
Ah,
Yes, sir.
okay. Oh, thank you very much. Yeah. Uh, so, who introduced me? That was Ronak Shah.
Yes, sir.
Okay, Ronak Shah, thank you very much for the kind introduction and invitation to this presentation.
Thank you, sir.
So, what are your background of these 62 people? 62 people. Are they all teachers or students?
All faculty members from various institutes in
Uh,
India, from India.
okay. What is their background?
Uh, Mechanical engineer, most of, and then chemical engineer and electrical engineer.
Okay. Mhm. So I have a small presentation here on low temperature fuel cells. I will just take you through that presentation. If you have any questions, you can interrupt me. I will answer those questions. Okay. So I'll try to. Yes, yeah, am I audible to you, or I need to raise the volume? Can you hear me properly?
Yes,
Yes, sir.
Okay. No problem.
it's okay.
So, yeah. Okay. Good. So let me talk about low temperature fuel cells. So the idea of fuel cell came up because of this man whose name is William Grove. So if you look at this diagram, what they have done is a very huge fuel cell, like the computers that we had in the 1960s and 70s, where they used to go with a punching card. In a similar way, what they have done here is each of these vessels has two inverted test tubes, and these test tubes are supplied with hydrogen and oxygen. Each of them has, each of the cell has a hydrogen test tube and a oxygen test tube in the inverted manner. And so they are all series connected in series. You have 4 cells. This was one of the first demonstrations of a working fuel cell concept, wherein they used hydrogen or oxygen. So, what is the limitation of this kind of a fuel cell? That is what we should first try to understand to appreciate how far we have advanced in terms of the technology of fuel cells. So, in this case, oxygen and hydrogen are gaseous, and the test tube is inverted in a liquid, which is most probably H2SO4, that is sulfuric acid, and the wire inside the test tube is platinum in both the test tubes. All these are platinum wires inside the test tube. So the oxygen comes in contact with the platinum wire inside this test tube, and hydrogen comes in contact with the next test tube. And that happens in every cell, oxygen and hydrogen in contact with the platinum wire, and they're all connected in series. Now, when oxygen comes in contact with the platinum at the electrode electrolyte interface, it reacts. And in a similar way, when hydrogen comes into contact with an electrolyte at the electrode electrolyte interface, that will also undergo an electrochemical reaction. And we will look into what are these reactions at a later slide. So when hydrogen oxidizes on platinum surface, which is in contact with an H2SO4 solution, hydrogen will give you 2 electrons and 2 H plus ions. This reaction is limited to just the interface of the electrode, electrolyte, contact area only. So that would mean just this small cross section of the cell area. So this was the most challenging part in developing a fuel cell, how to increase the contact between the electrolyte, electrode, and the fuel or oxidant. So that sort of a contact is called triple phase mountain. There is where most of the refinements has happened and improvement in the fuel cell technology therefore. So before I go to details of fuel cells, I will explain the different types of fuel cells here. They are alkaline fuel cells. This is based on the operating temperature, the temperature at which the fuel cell operate, and depending on the nature of the electrolyte that is in use. So you have alkaline fuel cells, polymer electrolyte fuel cells, direct methanol fuel cells, and phosphoric acid fuel cells, molten carbonate fuel cells, and solid oxide fuel cells. They are in the increasing order of their operating temperature. Alkaline fuel cells, for example, use sodium hydroxide or potassium hydroxide, and it operates in the temperature range of 60 to 90 degrees centigrade. And PEM fuel cells, on the other hand, use a polymer electrolyte membrane. PEM stands for polymer electrolyte membrane. FC stands for fuel cell. A stands for alkaline. The MFC means direct methanol fuel cells, where D stands for direct methanol fuel cells. And they operate in the range of temperature 60 to 90 degrees centigrade. On the other hand, phosphoric acid fuel cells is in the range of 180 to 220 degrees centigrade. Molten carbonate, that means Na2CO3, K2CO3 kind of mixtures are made and they are melted. And you have a molten electrolyte, which is in operation. And that requires a higher temperature in the range of 500 to 600 degrees centigrade. SOFC is solid oxide fuel cell, where the oxide ions are conducted from one side of the cell to the other side. And they operate even at higher temperatures, which is in the range of 800 degrees centigrade to 1000 degrees centigrade. The fuel that is typically used in all these fuel cells is hydrogen normally. Sometimes it has some content of CO2 and CO if you are producing the fuel by a reforming process. Or in the low temperature fuel cells, you will be using pure hydrogen without contamination of carbon monoxide in the fuel mix. Because the CO in the fuel mix can seriously poison the catalyst on the anode side, and therefore the fuel cell will eventually show the deterioration in performance over time. So what I conclude from this slide is the fuel cells operating at high temperatures can tolerate a bit of carbon dioxide, but fuel cell operating at lower temperatures prefer to have extremely pure hydrogen as the fuel. So one of the processes that is used in fuel cells is the reforming process. Either you can reform the fuel, for example, methane, in external reformers, or you can reform them internally within a cell if it is operating at high temperatures, like the one SOFC, for example. You can have internal reformation there. So this is the typical diagram. Either you will produce H2O and sometimes CO2 or CO as products. And so oxygen, this is showing the direction of the flow of fuel product and the ion that is transported from one side to another. For example, in a DMFC, H plus ions are produced by the oxidation of methanol, and those H plus ions travel to the other side of the cell, which is a cathode, where it comes in contact with oxygen to produce water. On the other hand, for example, hydrogen, or for example, in alkaline fuel cells, OH minus ions are produced at the air side, and they travel through the membrane into the anode side to react with hydrogen and producing water. So the transport of ions depends. If it is H plus ions, cations, they will move towards the cathode. If it is anion, for example, CO2 minus, O2 minus, OH minus, they all travel towards the anode side to react with the fuel in that location. So you have this type of dynamics happening internal to the fuel cells. It's important to understand this process. So fuel processing is an important issue for fuel cells. You can either start with liquid fuels or you can start with natural gas. The first step is to remove the sulfur content from the fuel and then send it to SOFC, thermally integrated reformer, which operates in the temperature range of 500 degrees centigrade to 1000 degrees centigrade. Or you can go down and to a lower temperature and then convert the fuel into hydrogen, H2 and CO. That is the reforming process. Use shift reaction. I hope you remember shift reaction. Any chemical engineer? Hello? Can you hear me? Hello?
You are audible, sir.
Yeah. I'm asking whether you know shift reaction or not. Maybe you don't interact. We conduct online courses. We used to have some interaction happening. Anyway, it doesn't matter. I will continue without interrupting the flow. So shift reaction, wherein H2O react with the CO molecule to produce hydrogen and CO2, happens in the range of temperature 300 degrees centigrade to 500 degrees centigrade. I have missed a C here, so apologize. And then you can selectively oxidize CO to produce almost pure hydrogen, which can be fed to PMFCs. They can tolerate up to 10 ppm of CO. On the other hand, phosphoric acid fuel cells can tolerate up to 5% CO. So what this indicates is the increasing complexity of fuel processing, and it causes a decrease in efficiency. This is a typical characteristic of a fuel cell wherein you plot the voltage that is obtained per cell versus current density. So every electrical device has a characteristic. So in this case, this is called an IV characteristic, something very similar to that of a solar cell, for example. And wind power, on the other hand, has not an IV characteristic, you say CP lambda curve, that is coefficient of power versus the lambda, the tip speed ratio. Okay. So the characteristics of a wind turbine is CP lambda. The characteristic of a solar cell is IV, the current potential curve. Fuel cell also has an IV curve. So what we have done here is plotting cell voltage versus current density. So you typically get in the range of 1 watt per centimeter square, or 1000 watt per 1000 milliwatt per centimeter, 1 watt per centimeter square, yes. So cell potential is in the range of 1.23 volt, and current density you get 1 ampere per centimeter square, in that range usually. So if you multiply the current density, say here ampere, milliampere, here this milliampere, so it will be 1 ampere, this is the peak maximum. So this will be about 1 into 0.8, so 0.8 watt per centimeter square. You get that much from centimeter square of the cell. And you have variety of losses, the losses that are caused by the cathode side reaction, that is oxygen reduction reaction, the resistance offered by the polymer electrolyte membrane, the resistance offered by the anode side, and resistance offered by the thermodynamic issues that starts from here. So you have a delta H for every reaction, that is enthalpy reaction, but that whole energy does not cause in a cell potential. In a running device, what is useful is delta G instead of delta H, and therefore even before you start a fuel cell, you have some thermodynamic losses. That is what's shown here. So 1.23 is the maximum voltage that you can gain at 25 degrees centigrade from a hydrogen oxygen fuel cell. So this is a typical characteristic of a fuel cell potential versus current density, as I have shown in the previous slide. These are comparisons of different types of fuel cells. That is, if you operate a fuel cell with pure hydrogen, that is the best that you have. With methanol, the oxidation kinetics is very slow, and therefore the power output decreases, or the current density at a given voltage decreases. And there is further reduction in the performance of the fuel cell when you feed the fuel cell with CO contaminated hydrogen. So, for example, you go to this current density, maybe around 200, in this 200 milliampere per centimeter square, you would notice that CO contaminated hydrogen has the lowest power density, or comparable to that of methanol, and then pure hydrogen has the highest performance. So these are typical characteristics of different types of fuel systems fed with different types of fuels into the same stream. Some typical calculations, maybe you can check these calculations. What is done here, you have calculated the delta G, that is the Gibbs free energy, is equal to change in enthalpy minus the delta S minus the delta S. This calculation is done for a pressure of 1 atmosphere pressure and 25 degrees centigrade with 1 mole of hydrogen reacting. If you consider that, this is the enthalpy that is released per mole of hydrogen, and the temperature and delta S minus 163.2. If you do this calculation, you get the delta G. And the cell voltage can be calculated by using the equation minus delta G by NF equal to delta E, or voltage of the cell. If you do this calculation for 25 degrees centigrade at 1 atmosphere pressure, you get 1.23 volt of the cell. At 80 degrees centigrade, the T delta S term increases, which has a minus sign in front of it, and therefore the cell voltage slightly drops, and the voltage calculated is 1.18 volt instead of 1.23. This doesn't mean that the cell worked badly. The voltage, there is a minor drop at the OCP, but the kinetics get improved when compared to that at 25 degrees centigrade, and it is much faster at 80 degrees centigrade, and you will be able to derive much better power output if you were to use the cell at high temperature. So in this case, it's a PEM fuel cell, and typical operating temperatures are in the range of 80 degrees centigrade. Okay, and so the fuel cell, you can say, is a voltage limited device that can deliver some power. The voltage is 1.23 volt, but the current density, the current as a unit area of the cell can offer is much higher as compared to a battery. For example, a lead acid battery or a lithium ion battery will offer in the range of 25 to 50 milliampere per centimeter square, but their voltage is in the range of 2 volt, or for lithium batteries it is in the range of 4 volt. Lead acid 2 volt and lithium ion battery is in the range of 4 volt. Fuel cells are in a different class of devices, electrochemical devices, which are mainly limited by the voltage. Instead of 2 volt or 4 volt with a battery, you get the fuel cells in the range of 1 volt, even less than that, 0.9 volt, I would say. But the current density, instead of 50 milliampere per centimeter square, you get about 1000 in that range. Or at least under practical conditions, when you run the cell at about 80 degrees centigrade with hydrogen and air, you will get a current density in the range of 500 milliampere per centimeter, which is 10 times than that of the batteries. But even with all these advantages with fuel cells, it did not work out as much as we expected. So we will run into all those reasons What is done here is to build a stack of fuel cells. You cannot run any practical device with a 1 volt power source. You need at least, I think, most devices will, LEDs will run with a 2 volt battery or so, or most of the devices needs laptops and mobile phone chargers in the range of 12 volt or so. So what is done is to stack cells together to get desired voltage. So if you stack about 12 cells, which are of voltage 0.9, you will get about 10 volt. And depending on the area, the power output will be decided. Usual area is in the range of 100 centimeters square per cell in most of the transportation applications. So the cell has consists of multiple cells, and each cell has a membrane electrolyte, and which is sandwiched between the two electrodes, that is the anode and cathode, as it's shown here. So hydrogen is pumped into the anode side and oxygen or air to the cathode side. So on either side of the electrodes, you have something called flow fields. These mark, for example, these are the flow fields through which the oxygen and hydrogen are transported to the electrode and subsequently to the catalyst surface for electrochemical reaction to generate electrons and the voltage. So that is how you build higher power systems with fuel cells. That means you stack cells in series and in parallel to achieve desired voltage and current densities. So if you have a single cell, the power density is given by voltage into current density, V cell into current density. Stack power output is given by voltage into current. That means the cell voltage into number of cells into current density and area. So if you do this, you will get the net power output of the stack. But stack won't run on its own. It will have many other auxiliary units to pump air, for example, to heat the cell to the desired temperature, to remove water, for example. So, and the whole control is there. The electrical circuitry that runs the cell, that controls the oxygen flow, that controls the fuel flow, etc. Cooling the cell. This takes out some part of the energy that is generated. So those are all auxiliary power requirements. And you have to subtract to get that power from the output power to get the net power output of the stack. So the power output increases with the area, larger the power output. Number of cells will also add to a higher power output. So this is one example. I think this picture is a very old picture. There have been several attempts to reduce the cost per watt hour, and it is too high for most of the applications. That's the reason we don't have realistic device yet in the market, that we cannot, we are still unable to go and buy it from the market. You only have test drives available, test vehicles, or you have only those kind of vehicles. Especially these are developed by some of the well-known automobile companies. Ford, for example, has a fuel cell vehicle. Toyota, General Motors, all these companies have test cars of this kind. Demonstration electric vehicles, you can say. These are based mainly on hydrogen, oxygen, polymer electrolyte based fuel cells, the electric vehicles. But DMFC, on the other hand, is developed for use in handheld devices like mobile phone, for charging a mobile phone or running a laptop, etc. One of the major issues with this kind of fuel cells is the cold temperature startup, and that is specific to cold countries like in Canada, for example, or in the Sweden, for example. We may not have such a issue, but still the rising the temperature to initial 80 degrees centigrade is found to be somewhat problematic. So now I'll take you through some of the components that are being developed at various labs across the world. Okay, so you have primarily three components that we need to discuss. One is the electrocatalyst that is used at the anode and the cathode. The other one is the membranes, and the next one is the hardware, that is the bipolar plates. So there are a lot of work happening around each of these materials. So all the low temperature fuel cells, we use precious metal catalysts. They are mainly based on platinum. The platinum is very expensive, something very close to or even more expensive than gold. So we cannot use that much of platinum. The cell will be too costly if you have platinum-based catalyst. So I started with a cell wherein you had two electrodes dipped into an acid-containing jar. That does not work that efficiently. So there are other configurations of fuel cell. For example, MEAs have come, membrane electrode assemblies, wherein you coat a thin layer of the catalyst to one side of the membrane, which is anode, and the other side of the membrane is coated with the cathode catalyst. The catalyst is typically platinum, but you don't use pure platinum. So platinum is typically supported on carbon surface, and you call that is carbon supported platinum. So carbon supported platinum may be 20 weight percent or 40 weight percent of platinum on carbon. If you have 100 grams of catalyst, 80 to 60 grams will be carbon, and 40 to 20 grams will be platinum on the catalyst. So that is used to oxidize pure hydrogen. The same catalyst is used in reducing oxygen as well. So when you have a PEM fuel cell that runs on hydrogen and oxygen, the catalysts are platinum on both sides. Anode catalyst and cathode catalyst therefore are challenging issues because of the main cost involved in buying these precious metals. So, for example, on the other hand, this is the comparison of catalyst loading in two of the commonly known low temperature fuel cells. One is a DMFC and the other one is a polymer electrolyte membrane fuel cell. In direct method fuel cell, you use a catalyst in the range of 5 to 10 milligram per centimeter square on both the anode and the cathode. Since you have methanol fuel in DMFC, you cannot use platinum as a catalyst because it gets passivated quickly with the CO that is reduced after dicing methanol. You go with a platinum ruthenium catalyst, which is an alloy almost in the ratio of 1:1, platinum to ruthenium atomic ratio. And ruthenium has this capability to form OIS species on its surface. These OIS species that is generated in situ can react with the CO that is formed by the electrochemical oxidation of methanol, and the OIS react with the CO to produce clean surface again. So platinum ruthenium is the CO tolerant methanol oxidation catalyst. Platinum will get poisoned if you use for methanol oxidation. So the loading in methanol fuel cell is in the range of 5 to 10 milligram per centimeter square. At the same time, the catalyst loading in polymer electrolyte membrane fuel cell, even with CO contaminated fuel like hydrogen, is in the range of 1 milligram to 0.5 milligram to 1 milligram per centimeter square. So you have an activation loss in the range of 0.3 volt for the anode, and for the cathode it is in the range of 0.3 to 0.4 volt. This means the theoretical potential for oxidation of hydrogen is 0 volt. That is why hydrogen is used as a reference electrode, and its potential is set at 0 volt. And we compare every other potentials with respect to hydrogen. So the hydrogen potential from 0 will go to almost 0.3 volt in an operating fuel cell in the positive direction. On the other hand, the oxygen reduction potential versus reversible hydrogen electrode is 1.23 volt, and that potential come down from 1.23 volt in a realistic operating fuel cell to 1 volt or so. So the net voltage of the fuel cell under operating conditions will be in the range of after subtracting for activation losses at the anode and at the cathode will be in the range of if you derive a current density of 100 milliampere per centimeter square will be 850 millivolt. Okay. So what are the challenges involved with the catalyst? They are highly expensive. Even though they catalyze the oxygen reduction reaction, still the process is very sluggish, very slow, and their durability is an issue. Platinum gets oxidized, ruthenium gets oxidized, their surface areas decrease. As a result, the fuel cell performance declines with time. So one of the objectives of today's research in electrocatalysis for fuel cells is to improve the catalytic activity and to develop durable and very active catalysts that can run into tens of thousands of hours. For methanol fuel cells, you at least target in the range of 25,000 hours, and for PEMS fuel cells, you need something like 1 lakh hours to be run in a realistic device. The other issue is, since the loading is very high, people are attempting to reduce the precious metal content without reducing the oxygen reduction reaction activity. Improve the methanol tolerant, because when methanol gets oxidized, CO is generated and they get adsorbed on the catalyst surface, and it causes a reduction in the activity of the catalyst. So there are attempts to improve the methanol tolerance of fuel cells. So this is a typical cell stack device. A lot has gone into designing and developing fuel cell stack. This one stack that I worked when I was doing my postdoc, during my postdoc years. So this is a model of that cell stack. Here you have bipolar plates. These are all the bipolar plates, and they are held between two end plates. This one end plate and this is another end plate. These are the inlets and these are the exit outlets. So you can supply hydrogen through this and take out hydrogen here, whatever is not reacted. There will be an overpressure to run the hydrogen through the cell. It may be recirculated, but you will not flow it in too much of an excess. In a similar way, you have oxygen that is flowing from here, and whatever excess, including that is not reacted, maybe nitrogen, if you are using air, for example, will be coming out through this exit or outlet. So if you talk about bipolar plates, it's better to have the thinnest of the possible materials, which are resistant to corrosion, because these are electrochemical devices. They have acids in the concentration range of 1 molar, and it can cause severe corrosion to stainless steel and other such materials. So overall aim is to produce thin bipolar plates. What we use in the labs is dense carbon materials, carbon-based materials or graphite plates, but these are not so good for widespread applications because of the material is not that hard. It can easily break. So people are trying to develop thinner materials, and you cannot reduce beyond a certain thickness with carbon-based materials. So the overall attempt is to reduce the mass and volume of the fuel cell stack, and to reduce the electronic resistance, which cause an ohmic drop with the power output. So conductivity of the bipolar plates can make a significant difference in the high frequency resistance, that's the impedance, and the stack output. So a simple calculation is given here. For example, a 22 centimeter square cell passing a 2.2 ampere current, a highly conductive bipolar plate material may only contribute to 0.025 ohm centimeter square, while a poorly conducting bipolar plate may contribute as much as 0.3 ohm centimeter square. This is equivalent to a Purcell voltage loss of about 30 millivolt or a power loss of 60 milliwatt. So what are all the other challenges in the materials development? The membrane that is used in fuel cell is the Nafion. Nafion is produced by DuPont. DuPont is an American company, chemical company, and DuPont membrane, Nafion, is based on a fluorine compound whose structure I will show you. It has a polymer backbone to which there are pendant chains of tetrafluoroethylene chains, which is attached to SO3H groups. So there's something like a moving or fixed S2, SO4 onto a chain of polymer. So this is the electrolyte that you use. But because of the fluorine content and proprietary nature of the material, it is very expensive. So there are many attempts to develop alternative membranes which are cheaper, which are not fluorine based, and which are also highly conducting and durable in nature. So people are trying to develop alternative membrane, but so far nothing has come up that can beat the performance of Nafion membrane from DuPont. They are of the thickness of about 0.3 mm or so, very thin membranes. They are not that thick. They are cast into thin membranes because if the thickness is too high, it can add to the ohmic drop of the electrolyte membrane. New electrocatalyst materials that enhance the low temperature methanol oxidation activity for anode. That includes many different types of alloys. For example, in those days, they were trying to develop platinum ruthenium osmium alloy, platinum ruthenium, and other precious metals were added to improve the catalytic activity of platinum ruthenium. But platinum ruthenium is one of the best active catalysts for alcohol oxidation. At the same time, cathode catalysts were also developed, and mainly again alloys, platinum iron, for example, platinum cobalt has been investigated thoroughly, platinum chromium, platinum nickel, many types of alloys are investigated for improved oxygen reduction activity. So there is activities in the membrane side, that is the electrolyte, and there is also activities, research activities to develop improved materials at the anode and cathode side as well, in terms of developing electrocatalysts for the fuel oxidation and for the oxygen reduction reaction. Many new concepts came along. This is one such a method wherein you can attempt to reduce the catalyst loading. So what is shown here is a cobalt gold alloy, not a practical system, but the concept is explained here. Gold itself can be expensive, but instead of gold, if you have copper, that will be much cheaper. So that such catalysts are also developed. Platinum, copper, partial materials. So the blue one is palladium, and inside you can have copper, for example, and then have these yellow bolts as platinum. So thereby you're limiting the precious metal usage to the surface of the catalyst, and the interior is mostly with transition metals like cobalt or copper or something. It's a model catalyst, and therefore they could use gold or palladium here. They are just trying to establish the concept here. This has been an area of very high level of research in the last few years, and they came up with this sort of a volcano curve where the activity of the catalyst is plotted versus binding energy of the species that is absorbed on the electrode surface. These are called volcano plot. So for example, platinum falls here. Okay, it has the optimum binding nature to the surface. There are two issues. If it does not bind well, the reaction will not happen. So such kind of species fall in this side of the volcano, I think. And if it binds too strongly, for example, ruthenium will bind very strongly and it will form a hydroxide permanently there. So that will damage the catalyst itself. As per Sabatier principle, you need an optimum binding of the reactant to the catalyst surface for the best performance output. So here will be platinum, most probably, I think. And that interacts with the oxygen, not too strongly and not too weakly, so that you have an optimum binding with the catalyst surface for the reaction to happen. So these things are attempted to reduce the catalyst cost and to improve the catalytic activity. So that is the model system. This is the way people attempted to produce such kind of catalyst in bulk. So this is a work by Sobel et al. Where they did the transmetallation reaction. They produced CO nanoparticles, put it into platinum complex. This is a mess. I don't remember the expansion of HFAC. I think something acetate. Okay, this is they use this organometallic of the platinum mixed with cobalt nanoparticles, and you get a platinum coating on top of the cobalt inner core. Such alloys are called partial nanoparticles. It's not alloy, partial particles. Alloy supported on removable support followed by heat treatment. So these catalysts are produced on the surface of silica, SiO2, and you leach the SiO2 out of the material, and you get CO coated with platinum by this sort of a seed mediated growth or transmetallation reaction. The other method is to develop platinum copper alloy, for example, and then de-alloy. When you de-alloy, copper gets dissolved in the acid and you have a highly porous platinum surface exposed. In this way, you can increase the area of the electrocatalyst. And this is called de-alloyed catalyst. This is also sometimes de-alloyed catalyst, sometimes they are called partial catalyst, depending on what is there left in the core. This work was developed by Peter Strasser. We also have done similar kind of work here in 2012 or so. Every metal has a crystallographic orientation on its surface, which we call H-scale indices. So platinum has, for example, 100 orientations, 110, these are called low index crystallographic orientations. And platinum 111, 100, and 110, for example. These are the most common surface orientation, crystallographic orientation on the bulk platinum surfaces. Their activities are different because their strength of their interaction with the reactants are different as we move from platinum 111 to 100 to 110. For example, this is the HUPD reaction, that is the formation of hydride on the platinum surface. Typical feature that you get when you record a voltammogram of a platinum surface. So here you have three different peaks corresponding to three different orientations of platinum. So what does it mean? The energy that is required to produce an adsorbed H on platinum 111 surface is different from that of a platinum 10 surface. These two are different from that of platinum 110. So the surface reactivity depends on the crystallographic orientation of the material. This is not just with platinum. Any metal will exhibit a similar kind of structure sensitivity or dependence on the crystallographic orientation that is exposed to the reactant. So this is to illustrate that, and as a result, many people try to develop shape-controlled nanoparticles. That means you produce particles of certain selected shape, wherein you have a prevalence of a selected orientation. Say, for example, 111 or 100 on maybe cubic surface or tetrahedron surface, or there are many different shapes of the particle that is reported in the literature. So these people, Zhang and Stam and Kovic et al., established such kind of reactivities of oxygen reduction reaction in HClO4 and H2SO4 electrolyte medium, and such kind of variations in reactivity are based on the surface orientation which is exposed is called structure sensitivity. And this is widely exploited these days in the area of electrocatalysis for hydrogen oxidation, for example, or hydrogen evolution, and for oxidation reactions, etc. So if you move on, so that much is about the membranes, sorry, the electrocatalyst part of it. And now I'll give you some hint on what is these membranes that we are using. So the membrane that I mentioned is Nafion membrane. Is unique but very expensive. So this is the backbone of the membrane, CF2, okay, this is tetrafluoroethylene polymer. That is the Teflon that we use as the cutting pad at our home, vegetables, etc. we use, right? So that is the Teflon backbone, to which these are like the pendants that girls or women wear. The pendant chain, this is called OCF2, CF3 is a pendant chain, onto which you have a OCF2, SO3H group. So this kind of polymers with the repeating monomers are constituting the Nafion membrane. So long chain of backbone onto which you have this kind of side chains hanging around. So this is the only conducting part. This gives mechanical and structural integrity to the membrane, the shape of the membrane. So we have this shape because of our bonds. Similarly, membrane is of this kind of thickness, of this kind of tapers, and this backbone gives the shape to this kind of a membrane. And SO3H is the conducting part. They get hydrated, so that is what they are trying to show here. This is polarized and large number of water molecules come and accumulate around it, and the H plus ion get dissociated, leading to SO3 minus and H plus. This H plus move to H2O, producing H3O, which is called the hydronium ion, and that is the conducting pathway for a Nafion membrane. So dry membranes will not conduct. You need the help of water molecules. So always Nafion membranes is used in a hydrated form. So this shows the water channels and the solid membrane phase. So this is the exploded view of this part, for example. Okay. So the membrane conducts H plus ions by the growth mechanism. H plus ions get dissociated here, move on to an H2O molecule. From there, it jumps to a nearby H2O and the transport continues. So water has a significant or important role in the transport of H plus ions. Another membrane is Flemion. I think this is a Japanese-based membrane wherein you have just replaced, almost similar to Nafion, Flemion. You have, instead of SO3H group, you have COOH, carboxylic acid group. But these are not that stable, and they are also not as conducting as SO3H based Nafion. But this membrane called Flemion was also, I think they used these kind of membranes in electrolyzers long back. There is a company called Ballard Power Systems, or you can buy fuel cells from Ballard. Ballard is located in Canada, and they work in close collaboration with the DuPont for membranes and Johnson Matthey in the UK for catalysts. Those people developed a few number of membranes. They are shown here. For example, phenyl quinoxylene. BAM is Ballard membrane. Okay, Ballard anion exchange membrane. It's a series membrane that they developed. Phenyl quinoxylene. These are, unlike CF2 backbone, you have benzene-like ring shape for the backbone. This another backbone, diphenyl 1,4-phenylene oxide, which is sulfonated here. Sulfonate group in all these membranes are the conducting species in that. The benzene ring is the backbone. Another membrane is the CF2 as in Nafion, and then a benzene ring pendant chain, which is sulfonated, type fluorostyrene-based membranes. BAM, Ballard anion exchange membrane, third generation. So Ballard has developed a large number of membrane candidates, but still what is popular in the market is Nafion. Most people report their data even today with Nafion. Other types of membranes were also developed, sulfones. For example, I think this is a sulfone membrane. Yeah, polyether ketone, polyadyl ether ketones. These are all different classes of membranes, for example. This is our Nafion membrane. These are examples of other categories of membranes. Yes, SO2 is sulfone, I think. Aryl ether ketone membrane, aryl ether sulfone, aryl group is here, aryl ether group is here, aryl ether sulfone membranes. And this is pure sulfone membrane, sulfonated. So you have different types of very complex organic molecules. If you don't understand organic chemistry, don't worry. What it says is that you have organic, highly aromatic backbones and alkaline backbones, to which the acidic group is attached to produce conducting membranes. So what we are familiar with is electrolytes that are in liquid state. For example, sulfuric acid in our lead acid batteries, potassium hydroxide or sodium hydroxide. These are the electrolytes that comes to our mind quickly when we talk about electrolytes. But there were also attempts to develop solid electrolytes, polymer-based electrolytes, etc. So polymer electrolyte you can treat as a solid electrolyte. Another example for a solid electrolyte is the yttrium stabilized zirconia, which is used in solid oxide fuel cells. So all these fuel cells require hydrogen, that means sustainable hydrogen. So what is the source of this hydrogen? You can produce hydrogen from different sources. The renewable sources are indicated here. That is from biomass by gasification or biohydrogen production. Wind energy used in electrolyzers. So you have to power the electrolyzer with the electricity to produce hydrogen and oxygen. That means when you have wind energy in excess, you supply to an electrolyzer to dissociate water and store the hydrogen and oxygen in separate tanks, which later on can be fed to a fuel cell to produce water and hydrogen. That is what wind electrolysis means. Same way with solar electrolysis, you produce electricity from PV panels or solar cells, use that to electrolyze water and store the hydrogen for times where you don't have light, and you can run it using a fuel cell. That's the idea many people are talking about. I don't know how practical or how cost effective such kind of proposals are. But I have seen such kind of talks in the books and with many experts, but I don't know whether they will come at all. And you have other ways of producing hydrogen, for example, from natural gas, reforming, partial oxidation, from coal gasification, in-situ gasification, including CO2 sequestration. So gasification is a chemical process wherein you can produce hydrogen, or reforming process. All these methods are available for producing pure hydrogen. So the key elements in hydrogen economy is infrastructure are given here. First, you need to produce hydrogen. Hydrogen is an element in the molecular form H2, which does not exist in the nature as it is. There is limited quantity of hydrogen, very negligible in the atmosphere. So you need to produce that. Once you produce it, there are two tasks involved with the production of hydrogen. One is how to store. Of course, you can store hydrogen in pressurized cylinder. The safety is an issue. The pressure has a limit. Explosion can be dangerous. And there is a limit to storing this hydrogen and putting in a practical device. So people do demonstrate vehicles with a small cylinder, but for long driving ranges, this can be a hurdle and a safety issue. Delivery is another issue, and then the conversion happens. The conversion usually, the device that is used here is the fuel cell, and it goes to applications to drive a motor vehicle or to drive a laptop or something. So these are the various elements of a hydrogen economy infrastructure that most people are talking about these days. Other ways of storing hydrogen are the large number of compounds for storing hydrogen, but I don't think you have any practical hydrogen storage material as such so far. I think what is maximum reported is 5% storage by weight. So many metal hydrides, magnesium nickel hydride, magnesium hydride, sodium aluminum, that's a chemical hydride, but these are all interstitial hydrogen storage alloys. And so people are working on developing hydrogen storage materials, organic framework molecules. There are many type of carbon nanotube, for example, lithium borohydride, but it's a compound. So hydrogen storage is a challenging issue one can think of. These are the other structures that came up in the literature recently. All sort of fancy structures, metal organic framework, which I mentioned in the previous slide, and of course carbon nanotube that is used everywhere and for anything. I don't know what is their promise as far as storage is concerned. I think they report in the range of 2 to 3 weight percentage of hydrogen in this sort of materials, which is not sufficient, not enough for any practical applications. So you primarily have 3 losses in a running fuel cell device. They are called activation losses. That is due to electrochemical reaction. Ohmic losses, that is due to the losses related to charge and ionic transport losses. And ions are transported from one side of the electrode to the other, electrolyte to the other side, and that causes ionic transport losses. And electrons are flowing through the electrode, and that causes electronic losses. Ionic losses are there, and typically ionic losses are much larger than the electronic losses. So you put these two together and call it ohmic losses. You have primarily, and then you have concentration losses. That means as the fuel cell runs, the fuel concentration and oxidant concentration, that oxygen concentration at the cathode can decrease depending on the power that you are drawing out of the device. This can cause a concentration gradient at the electrode surface, and that ultimately results in concentration losses. So you have 3 primary losses: activation losses, ohmic losses, and concentration losses. Activation losses are due to electrochemical reaction. Ohmic losses are due to ionic and electronic losses, conductivity losses, and concentration losses are due to not so sufficient enough reaction supply. So these 3 different types of losses are there. So to measure the real voltage of the fuel cell, what you typically has to do is to take the thermodynamic voltage, that is the minus delta G by NF. From that you can subtract at every current density the activation loss, that is this one. Activation means how much voltage is lost because of the activation process. That means the reaction that is happening on both sides. You have to apply an overpotential for the reaction to proceed in the desired direction. You will have an activation loss for the anode side, and you will also have an activation loss at the cathode side. So this has to be subtracted from the thermodynamic potential that you calculate. Similarly, ohmic drop you have to subtract, and the concentration loss that you have to subtract. When you subtract all these, you will get the real voltage. So eta is the activation losses. If you do this, you will get this sort of performance curve. This is the background to it. So here is where your ohmic drop is involved in this linear range. Okay, the activation losses are mainly in the high voltage range, and the mass transport losses are somewhere in the very high current density region or low voltage regions of the IV curve or IV characteristics. Okay, so that is about membranes and hydrogen storage and different types of losses. Yeah, this is about conductivity and resistivity measurements of the membrane. I'm not going into this much. It needs more time. I will skip on this slide. How you can calculate the ohmic drop. Okay, that is the electronic and ionic losses, and you can calculate the ohmic drop of the cell. That is from the linear part of the cell. You can characteristics of a fuel cell charge transport. The charge transport linearly decreases with fuel cell operating voltage. Okay, resistivity is given by this typical electrical equation. I'm not getting into this right now. Let us leave those parts. This is one of the equations that explains the kinetics at the anode and cathode side, which is called the Butler. I have inserted a space here by mistake. It's an overpotential. Okay. So this is called Butler-Volmer equation. One of the term is anodic term, and the other term, this is cathodic term, since there is a negative sign here, and this is the anodic term. So depending on the overpotential that you're applying, E minus ER is the overpotential. One of these terms will dominate. Okay, so for example, overpotential on anode side will yield this. Okay, and the other term will go to negligible values. That means anode overpotentials are typically positive voltages, and you have a minus sign here in the exponential. That minus sign makes this whole term negligible. On the other hand, for an anodic process, the overpotential is positive, and therefore this term will be positive, and therefore this term overall dominates for a hydrogen oxidation reaction. So this is called Tafel equations, Butler-Volmer equations, etc. If you have at high overpotentials, one of the limiting conditions of Butler-Volmer equation, which you might see in the fuel cell or electrochemistry textbooks. So those who want to get to know more about these things can refer to a textbook called Bard and Faulkner. Some of you may have studied this as a part of your BTech curriculum. I don't know. We teach them here. At least some chemical engineers should have seen these sort of equations in their UG curriculum. You can use fixed law to calculate the current. So these are used in calculating the flux of the reactant on the electrode surface, and this can be directly converted to the current on the electrode surface. For example, if it causes a concentration gradient, you can substitute what is the concentration on the electrode surface versus that on the bulk of the electrolyte. The surface concentration versus, I think, bulk concentration, and this is a form of the Nernst equation with and without concentration gradients. If you take the difference between them, you will get delta V equal to RT by NF. You're just calculating the electrode potentials for two concentrations and taking the difference to calculate the delta V. Okay, so that's what you have done. You can calculate in that manner. So I will skip all this. There's some schematic of a solid oxide fuel cell, which I have explained at the beginning itself. So I will not elaborate on this much. You may try to remember that this operates in the range of temperatures, 1000 degrees centigrade. Mostly this work comes from Japan. They are experts in solid oxide fuel cells. And even Toshiba had a very strong activity with phosphoric acid fuels and solid oxide fuels, Sanyo or some company like this, for a very long time. This fuel cell, phosphoric acid based fuel cell, was there in BHEL. If you have worked in Hyderabad R&D Center, they had got one 200 megawatt system, I think. Yeah. So these are the operating principles of a solid oxide fuel cell. electrolyte interface, for example. This is the yttria stabilized zirconia, which is used in solid oxide fuel. This is an example for a solid oxide electrolyte material used in YSZ, yttria stabilized zirconia. This is instead of the membrane, Nafion membrane. This is what you use for as an electrolyte in SOF phase. So there I conclude. Thank you for your attention. Do you want me to continue, or if I have more time, or I should stop? I don't know.
Thank you, sir.
If you have any questions, you can ask.
Some question from participant.
Yeah, please. Go ahead.
One of them, which conductivity effects more on the fuel cell, ionic or electric conductivity, to enhance the performance of fuel cell?
Can you repeat the question once again?
Yes, sir. Which conductivity effect
Okay, both conductivities are important.
more on the fuel cell, ionic or electric conductivity, to enhance the performance of fuel cell?
Untitled Chapter. So both conductivities are important. See, it is so when you oxidize a fuel, it produces, for example, hydrogen. When you oxidize, it produces H plus ions and electrons. H plus ion has to move through the electrolyte to the other side of the fuel cell, that is the cathode, and the electrons has to flow through the bulk of the electrode through the external fluid to the cathode side and to the reactant. So if your electrodes are not so electronically conducting, it will cause a severe ohmic loss. The same way, if the membranes are not sufficiently conducting the ions, that will also cause a voltage drop. So what it means is that you should have both electronic and ionic conductivity. Electronic conductivity for the electrode and ionic conductivity for the electrolyte, very high. Not mixed conductivity. Okay, this should not be mixed conductivity. That will short circuit the cell. That will be the problem. Yes, continue.
Our second question. Is any material available with high mobility of ion with high density of material? Is any material available with the higher mobility of ion with high density of material?
Currently, what you have is the Nafion. If you are asking about solid electrolytes, people are attempting to develop, but there are one or the other issues. If its ionic conductivity is high, its mechanical strength is very poor. Okay, if its mechanical strength is very high, they have other issues. They may transport the water too much from one side to other. So you have a large number of properties to come together when you talk about an electrolyte, which is, oh my God, 1 second. I'm getting a repeated call. I don't know why. 1 second. Yeah, continue with your questions.
Okay. Third question. How much is safe to have hydrogen fuel filling station, and what kind of operational safety will be required?
Yeah, 1 second. Hello? One second. Sorry. Yeah, so operational safety is an issue, but you have a large number of demonstration units across the world. Hello? Hello?
Okay, sir.
Okay.
Okay.
What happened?
No problem, sir.
Oh, yeah, I'm sorry. So operational issues are there, but you have these sort of refueling stations at most of the fuel cell developers. If you go to BMW, for example, in Germany, in Munich, or to GM in the US, they have come up with highly safe hydrogen fueling stations. That's not an issue. The issue is when it is put into the vehicle. once it is in the, we know how to handle hydrogen. We do handle a large quantity of hydrogen for many other industrial processes. The problem comes in once you fill it and put it into the vehicle, in a moving vehicle. If the cylinder explodes, or if the pressure is too high, or if there is a collision between two vehicles, then it becomes highly dangerous. In a stationary place, I don't think this is much of a problem as of today. I don't know what will happen when you scale up the number of such stations and when you mass produce such kind of hydrogen fuel vehicles. Otherwise, what I think the danger is once it is put into the vehicles.
Okay, sir. Thank you.
Thank you, sir, for your speech on today's session. I, Vaishal J. Banker, on behalf of the entire Mechanical Engineering Department, ADIT, Principal ADIT, Patel, and AICTE, would like to express our sincere thanks to you, sir, for accepting our invitation and giving us an excellent coverage on the low temperature fuel cells. We thank you for sparing your valuable time. And with this, we end today's session on the FDP of Green and Sustainable Technologies in India, the first session. Tomorrow, there will be the first session by Dr. G.N. Tiwari, sir. He is a professor at IIT Delhi. The session will be starting at 10 a.m. in the morning. So I would request all the participants to join in at about 9:55 p.m. With this, we end today's session.
Okay, Ronak, I have a few words to tell you.
Sir.
Thank you for the invitation. You have been calling me repeatedly on my landline. I appreciate your efforts to organize this. I'm talking to a screen and it has its own deficiencies. Okay, even in our classes we do interact, but I think these participants are at various places and you may have your own difficulties in making a direct interaction with them. But I am very much thankful to those who attended to me. I sincerely appreciate your time in listening to me. Thank you very much.
Thank you, sir.
Thank you for the invitation also.
Thank you, sir.
Take care. Bye-bye. Be
Bye.
safe.
Thank you, sir.
Okay.